Welcome back. Now we will continue working with the exact method from 2.5, following up on our introduction to partial derivatives. First, the exact method uses variables x and y where we've traditionally used x and t. And the reason is that it comes from describing the autonomous system dy dt equals negative mx and y. And dx dt equals n of x and y. What does this describe? Well, we have no t explicitly shown on the right-hand side. That's why it's autonomous. And each of these slopes depend on themselves and the other variable. So, how do we deal with this system? Well, the first thing we can do, since t is not explicitly shown, is form dy dx by taking the ratio of dy dt and dx dt to give us negative m of x and y over n of x and y, where both these m and n are just functions of the two variables. Once we have this differential form, this derivative, we're going to separate, just like the separable method, we first separate by multiplying the dx on one side, n on the other. But we end up with n as a function of x and y, and m as a function of x and y. They're not separated necessarily. So we bring them back together again. It's a little bit simpler in this form. And we have m of x and y dx plus n of x and y dy equals 0. Now this particular form is called a differential form. We have the slope form, where you solve for the slope. We had the standard form with linear equations, and now we have the differential form. Now this differential form compares directly to the total differential, which we get from calculus. If you have some function of two variables equal to a constant, then if you take the total differential of both sides, in a sense we used a shorthand of thinking of x and y in terms of t and differentiating down. But the total differential is simply the change in x, the partial derivative of f with respect to x, times that small dx, plus the change in y, partial of f with respect to y, times that small dy. All that added together equals 0 because the function was originally set to be a constant. Now this idea is covered a lot more in Calc 3, but we're using some ideas from it in this class. So let's look at how it corresponds. We have a total differential in terms of m and n. And from the f form of it, these correspondents, m and n, should correspond to the partial of f with respect to x and the partial of y with respect to, partial of f with respect to y. That's what we want. So we do need to verify that the m and n are both different partials of the same function to allow us to undo the total differential and get back to the function f of x, y. That is the goal. Once we get into the right form, we integrate back each partial and compare to get back to the total f. Okay, so what's the procedure? Well, first we check. In this case, we have an additional form of the check. We first want to get it in this differential form if it's not already there, and then we take the y partial of m and check to see if it's equal to the x partial of n. Now, why do we do that? Well, we want m to be our x partial, and we want n to be our y partial. And if we take the y partial of m, that gives us an x partial, then a y partial. And if we take the x partial of n, it gives us a y partial, then an x partial. Those are the same partials, just mixed in their order. And by Clairaut's theorem in the previous video, we know that mixed partials are equal as long as the function is sufficiently differentiable. So that is our check, taking the partial derivatives of the pieces we have in terms of the other variables. So you see the thing next to dx, you take the y partial of it. You see the thing next to dy, you take the x partial of it. If those two things are equal, you're good to go. What do? First, you partially integrate one or the other. It doesn't matter necessarily, but for you, it might be easier to do one or the other. Now, I do say easier with asterisks because often if you integrate the component that has a sum of multiple pieces, you get more out of it than if you were to integrate maybe a term that just has one component. And then once you've integrated one of them, you differentiate your formula solution back in terms of the other variable and compare. So using both pieces of information, m and then n, or n and then m. And it's up to you what order you choose that. But once you've done that, you're able to reconcile the form of it and find all the unknown functions, and then you can combine into an implicit solution as f of xy equal to c. Now notice that this is an interesting way to write a solution. We're really solving for the constant. This is a very strange way to do it. But for many, there are more differential equations that have solutions you can solve for the constant in than there are solutions where you can solve for the dependent variable. So this gives us a little bit more, quite a bit more freedom in terms of how we can solve the differential equation into a single form. Let's do a quick check. Here we have an example written in differential form where the dx multiplier is our m, negative 2x cosine of y, should be familiar, and then our dy multiplier is our n, x squared sine of y plus 2y. So let's check to see if this is exact. So we take the x multiplier and take the y partial of it. Differentiate in terms of the other variable. So the cosine of y gives us a negative, canceling out this one, and sine of y. So 2x sine of y. On the right-hand side, x partial treats the x as a variable and the y as a constant this time. So the x squared goes to 2x, and we're left with a sine of y. Since those are equal, we know that this is an exact differential equation, and we can solve it using the exact method. Okay, so let's clean up some things so that we can go through the process of solving this problem. Okay, so now that we've summarized all the information we've done so far, note I have the m defined as the x partial and the n defined as the y partial, so I know which components I'm comparing together. To integrate, I can choose either one, but it is more helpful to choose the term with more things added, so that your first integration step does more of the work and you don't have to do as much the second time. So f is equal to the integral of n dy. What is that? That is x squared sine of y plus 2y. Now, since we're integrating in terms of y, that means we're treating x as a constant, just like a partial derivative. It's a partial integral. So we will have the sine integrating back to a negative cosine, and y integrating back to a y squared. X squared is a constant. Now, every integral has a plus c, but this particular one treated x as a constant, so that plus c is actually a function of x. So that's why I say you get the form of the solution. You don't know if there's any other x functions left over. So now we differentiate. partially. Well, what do we differentiate in terms of? In terms of x. Because we integrate in terms of y, we differentiate in terms of the other. Partial. In terms of x of this function. First, we treat y as constant. That gives us negative 2x cosine of y plus 0 plus c prime of x. Because c is a function of x, we get a derivative. And that should equal m, which is the x partial, which is negative 2x cosine of y. And hopefully you have a few things that you can cancel out. If you don't, you're in trouble and you should probably start over. So let's check. Those two are the same. They cancel, which leaves us with c prime of x is equal to 0. And the only way c prime of x can be equal to 0 is if, after integrating, we get a constant. So you may think, wait a second, well, okay, to be more careful, if you want to be more careful, you can always say something like, this is c1 of x, and then this is a c2. So the constant function of x is actually just a constant. Or you can just use c, it's fine. And then the third step, we combine together the information we know. What does f equal? It is negative x squared cosine of y plus y squared, which we found here, plus c of x, which is really just plus a constant. And we're going to throw that constant over to the right-hand side to get our implicit solution. Now notice, could we have solved for this in terms of y, the dependent variable in this case? No. It's transcendental. We could have solved for x, but that feels kind of awkward. But this is an example of when it's very helpful to, instead of solve for one of the variables, solve for the constant by grouping all the unknowns together, or all the variables together. And one problem with this is we're not quite sure on how it's written which one is the independent variable and which one is the dependent variable. We'll have to kind of go back to the original problem to figure that out. But it is a way to combine information together in a succinct form.